Hands-on math.
Hello, this video provides some intuition about and examples using the fundamental theorem of calculus. Suppose we're given a function f of x, and it's a non-negative function, which of course means that it will be above the x-axis, and suppose we're interested in x values that are positive, although this would work with negative x values as well. So the graph would look maybe a little something like this. We're interested in understanding the area under this curve, and the fundamental theorem of calculus helps us do that in the following way. So let a of x equal the area under the curve f of x from 0 to x. Right, so the amount a of x, the value of a of x, for any given x, it would be like this amount. This area under the curve. So if this is our given value x. So as the idea of calculus might suggest, what we're interested in understanding a little bit is, well, we might want to know, how does this area value change if x changes, right? If x moves to the right, I hope it's pretty obvious. If x moves to the right, that area is going to get bigger, and so the value of that area function is going to change as x changes. To explore it, we could consider the derivative. The derivative a prime of x. Well, let's go back to the definition, the limit definition of the derivative, the limit as h goes to 0 of the difference quotient a of x plus h minus a of x divided by h. It gives us a definition for the derivative of that area function, and we'll describe how quickly the area function is changing. Well, in particular, let's think about the numerator of the difference quotient, the limit. I'm sorry, not the limit, just the expression a of x plus h minus a of x. And let's think about what that means. So that difference quotient, it introduces a second point here on the x-axis, x plus h. And so the difference between the areas would be the difference, would be the area of this blue shaded region. And in particular, if you think about this expression, right, it's not just the difference quotient, we're also interested in taking the limit as h goes to 0. Well, as h goes to 0, these 2 points, x and x plus h, are going to get closer and closer together because the difference between them is h. The difference between them is going to get smaller and smaller and smaller. So thinking about the limit, thinking about that part as h goes to 0, the limit is going to make this blue area smaller and smaller by moving the x plus h line closer and closer to x, to just x. Well, okay, so as that happens, as that line moves closer and closer, as the x plus h line moves closer and closer to just x, let's think about what this shape will look like. Well, it'll start looking more and more just like a slivery little rectangle right there at x, right? As h gets smaller and smaller and smaller, that region is going to get thinner and thinner and thinner. The width is always going to be equal to h, right? The width of that region is always just going to equal h, and the height, if you think about it for a moment, the height of that region is going to be the value of f of x. Right? As this line moves closer and closer, as h gets smaller and smaller and smaller, the height of that region is just going to be getting closer and closer to f of x. So we can, in a way, we can approximate the difference between those two area amounts by taking the height of a rectangle to be f of x, and the width to be h. And this is going to be true as h gets closer and closer to 0. It's going to be, this approximation is going to get better and better and better. Well, let's put that together. So a prime of x, the derivative of this area function, it's the limit as h goes to 0 of a of x plus h minus a of x divided by h. But if you believe what I just said, right, as h gets closer and closer to 0, this numerator is going to become more and more like, right, as we take the limit of h towards 0, this is going to become more and more like f of x times h over h. But of course, the h's now can cancel, and we get f of x. And it might not seem like it, but this is a pretty big deal, because what this is saying is that the function f of x has, so the function f of x is the derivative of the area function. Another way to look at it, the area function is an antiderivative of the function f of x. A of x is an antiderivative of f of x. And symbolically, that means that a of x equals the indefinite integral f of x dx for some arbitrary constant. So there's some antiderivative function g of x of f of x plus some specific c that gives us the value of that area function. So if I can take an antiderivative of my function f of x, there's some arbitrary constant that would correspond specifically to that area function. So let's think about an example. We know that a definite integral like the following, the integral from 1 to 4 of 6x squared dx. This notation, it represents an area amount. Specifically, it represents the area under that parabola. There's a parabola, y equals 6x squared. And we're interested in determining the area under that curve from 1 to 4. Right, so I'd like to know what this area is. We know the area function that corresponds to this example, the area function from what we just described, it's going to be an antiderivative of 6x squared. So if we add 1 to the exponent, we get 3x cubed. And then dividing the coefficient by 3, we get 2. And so 2x cubed is going to be our antiderivative. Of course, the area function, we have to kind of think about that arbitrary constant, at least for a little while. Some of you may know we can ignore it eventually, but we want to think about it now. Right? And so this function represents the area amount here. In particular, the area function evaluated at 4 represents something, right? It represents the area under the curve, but not from 1 to 4, right? This notation, if you think about what we talked about above, our area function described the area under the curve from 0 to x. So the area function at 4 represents all of this area from 0 up to 4. But that's a little more than I want. But it's exactly more by this amount, by the area between 0 and 1. So I can subtract the area function at 1. So let's do that. Well, this is my area function. If I plug in 4, I get 2 times 4 cubed plus c. And then I want to subtract 2 times 1 cubed plus c, but I want to subtract that whole thing. So this c becomes negative, and it's going to cancel with that c. And I'm simply left with 2 times 4 cubed is 64, minus 2 times 1, which means we have 128 minus 2, or 126. And that turns out to be our area amount. More generally, right, this process that we just worked through is called the Fundamental Theorem of Calculus. And to talk about that more generally, let's think about it. So if we have an integral from a to b of some function f of x dx, a definite integral, right, this represents, if f of x is non-negative, it represents the area under the curve, if f of x is non-negative on the interval from a to b. Well, this equals the difference between a function I'm going to call capital F evaluated at b and capital F evaluated at a, where capital F of x is any antiderivative of f of x. So to look at another quick example of the interval from 2 to 5 of, let's say, 10 plus 3x squared dx. Right, so this represents the area under the curve. This is a non-negative function on that interval. And there's a two-step process that we can follow to find the value of that antiderivative. To find the value of that integral. First, I want to find an antiderivative, and then I want to plug in the limits of integration, the 5 and the 2, and subtract. Well, an antiderivative is 10x plus x cubed. And now I've done the kind of the integral part of it, so I'm going to write a line to remind me that I want to subtract. So this is sometimes read such that I want to evaluate that expression at 5 and also at 2, and I want to subtract the difference. So working through the arithmetic here, so this is 50. That turns out to be 125, so I get 175. On the other side I have 20 and plus 8, so minus 28. So we end up with 147, if I didn't mess up my calculation. I think that's right. And there we have it. Thanks.